When I was learning reactions, I learned it like this. If there's no driving force, there's no reaction. I didn't know you could tweak things. You could tweak things by bumping up the concentration or doing this or doing that to get the reaction to go. I just learned, hey, no reaction. So no reaction is no reaction, but that's not always the case. But you don't want to tweak too many things, otherwise there's too many things to memorize, right? And so what we want to do is we want to keep things simpler. To keep things simpler, we'll just keep it under standard conditions, standard thermodynamic conditions, and then predict it. And then that's our base, that's our reference point. And then if we tweak things, then we'll just make adjustments based on those tweaks. There's one more complication, and that is thermodynamics. Thermodynamics doesn't tell us the whole story. In order to understand the whole story of a chemical reaction, we need to know the thermodynamics of it, and we need to know the kinetics of it. The kinetics is what we call the speed of the reaction. And so, for example, diamond versus graphite, which one's more thermodynamically stable? Which one's more stable? The more stable form of carbon is graphite. And that means, well, diamond's up here, graphite's down here. Nature tends to minimize energy, lower energy. And so that means the diamond should decompose into graphite. And so does that mean you shouldn't buy diamonds because eventually they're going to decompose into graphite? No. Even though there's a thermodynamic driving force there, we're going from less stable to more stable, it's not going to happen because the kinetics of this reaction is extremely slow. When we have extremely slow kinetics, we call it pseudo-stable or metastable. In fact, metastable is the word we use. Metastable means thermodynamically unstable, kinetically stable. An example of a metastable mixture would be this. When I leak out the methane into the air here, do I have to worry about a fire or an explosion? No, because it's metastable. It needs a spark or something to kick it off. Well, I'm not going to worry. There's methane in here. I'm not going to worry about any flame or explosion as long as there's no hot surface it comes into contact with that kick. And so we need something to give this a kick, and it needs a big kick to get this to decompose into graphite, which isn't going to happen. So diamonds are metastable. For us, we're going to ignore the kinetics. We're just going to look at the thermodynamics. Going from higher energy to lower energy, in terms of internal energy and in terms of enthalpy. For metathesis reactions, we're looking at, typically reactions of 2 or more ionic compounds. Like an AB plus CD, but it doesn't have to be 2. It could be 3, 4. It could be an AB plus CD plus EF plus GH plus I, etc. You can have any number of combinations. So, and it doesn't always have to be ionic compounds. Weak electrolyte molecular compounds can participate in metathesis, like ammonia and ammonia-like compounds. Ammonia-like compounds are called amines, and so ammonia and the amines can also participate in metathesis. But all of these, we're looking for favorable ion combinations. We want to find ions that like each other. Well, what ions like each other? In terms of theory, we just want to form more stable products. We want good bonds, strong bonds, right? But we don't want to get into the quantum mechanics of that. We just want something more descriptive. More descriptive would be in terms of, does a precipitate form? If a precipitate forms, those ions like each other enough to precipitate out of solution. A gas forms, it's good. The ions combine to form gases. Those gases can escape. And then finally, stronger acid to weaker acid. Stronger acids have weaker bonds, they're less stable. Weaker acids have stronger bonds and are more stable. And these are the types of things we look for. These are what we call driving forces. So whenever we're dealing with a metathesis reaction, we're looking for these driving forces here. So how do you know what the precipitates are? Precipitates are going to follow the solubility rules. Now, we started this yesterday. I didn't finish it. Let's finish it now. Group 1 and ammonium compounds are all soluble. I forgot where we left off. 2 If we do nitrates, what's this? Acetates and chlorates are all soluble. So after we look at the cations, we go to the anions. The first three categories of anions are soluble. The last three categories of anions are insoluble. And so the chlorides, bromides, and iodides are all, except for silver, mercury. Is this mercury 1 or mercury 2? Mercury 1 and lead 2. Interestingly enough, mercury 2 chloride is soluble. Lead 4 chloride is soluble. Lead 2 chloride is insoluble. Mercury 1 chloride is insoluble. Now, I asked you this yesterday. Where's fluoride? Why is fluoride not on this list? Or did I ask you this yesterday? Did you come up with an answer for me? Why is fluoride not on the list? Why isn't it fluorides, chlorides, bromides, and iodides? Uh-huh. Yeah, it's high charge density, which makes it what? Which makes it more reactive. You know, fluoride's small, and chloride's a lot bigger. And so this higher charge density means it's going to seek out cations more. You know, what we're looking at in metathesis is we're looking for cation-anion combinations. And so fluoride's got more charge density. You know, both of these are of the same charge, but the charge density is different. Fluoride has got more charge density, it's going to be more reactive. So if you're looking for the solubility rules for fluorides, the best thing is just to look at them individually. What you do is you go to a book. Now, if you're looking for solubility of fluoride, we look that up. Book like this. This would be the CRC Handbook of Chemistry and Physics. This book is about this thick. It's like 2,000 pages or something like that. And this has got a whole bunch of data. And so if you're interested in the properties of lithium fluoride, you go in here and you look. You can read the properties of lithium fluoride. And there are a huge number of entries. I forgot the exact number, but 200,000 entries or something. Well, do you want to go through and memorize all the properties? Like that question for the phosphate, maybe I should have memorized the properties of phosphate. No, it's too much to memorize. What you want to do is you want to look for these patterns, reactivity, this type of stuff, and then figure it out based on that. But you can look it up here. It'll tell you about the solubility of fluoride, different fluoride compounds in this. This is the Handbook of Chemistry and Physics by the CRC. This one is for inorganic, mostly, some organics. If you want organic and biomolecules, then typically what you use is the Merck index. This is a very thick book too. Merck index has lots of biomolecules and organic molecules in here. You can look up the properties of those as well. Or just Wikipedia. That's pretty good. All right, so fluorides are more reactive. Well, let's move on. Let's move on to sulfates. Sulfates are soluble except for silver, mercury 1, lead 2, calcium, strontium, and barium. What happened to magnesium? Why isn't magnesium sulfate here? Well, two reasons for that. You would think it would be, and so there's certain patterns. You got, when you look at this one, you can just memorize it. But after you memorize it, then you start thinking. Does it make sense to you, these solubility rules, or not? Well, let's continue on. Hydroxides. Hydroxides are mostly insoluble. Hydroxides are insoluble except for group 1, ammonium, calcium, strontium, and barium. Again, magnesium is missing here. But I know magnesium hydroxide. And it turns out that magnesium hydroxide is soluble or insoluble. It turns out it's insoluble. In fact, you can buy this. Magnesium hydroxide, you can buy it in some supermarkets. Have you ever heard of milk of magnesia? Milk of magnesia, it's like some kind of antacid, and drink it. And so magnesium hydroxide should be insoluble. And like group 1 hydroxide would be like sodium hydroxide. Sodium hydroxide should be soluble. Actually, sodium hydroxide is available at supermarkets too. Do you know where you find sodium hydroxide? Sodium hydroxide, they don't call it sodium hydroxide. Do you know what they call it? They call it lye or drain cleaner. Okay. And so you can find this like in the household products. They sell it as lye or drain cleaner. And so let's say you're at the supermarket. You're at the supermarket and you go to the supermarket, you're there to buy some milk magnesia. They ran out of milk magnesia. No more on the shelf. But then you see the sodium hydroxide there. Can you substitute sodium hydroxide for magnesium hydroxide? Is that okay? Well, both hydroxides. Well, they both should do the job. If you have an upset stomach, just go ahead and take the sodium hydroxide instead. Would you? What if I just cover up the label and don't call it drain cleaner or lye and just say that this is neutralize acid stuff? It should neutralize acid, sodium hydroxide. Same thing with magnesium hydroxide. Magnesium hydroxide neutralizes acid. But we would drink this stuff, but I don't recommend drinking sodium hydroxide. So if they do run out of magnesium hydroxide, find something else. Don't use the sodium hydroxide. Why? Are they both strong bases? Are both of these strong bases? No. Sodium hydroxide is a strong base, right? But magnesium hydroxide is not a strong base. Why? How about this? Iron 3 hydroxide. Iron 3 hydroxide has 3 hydroxides per formula unit. This has got to be a powerful base because it's got 3 hydroxides there. Is iron 3 hydroxide a strong base or a weak base? It's a weak base. Weak base, weak base, strong base. How about ammonium hydroxide? Well, ammonium hydroxide is not very stable. Ammonium hydroxide decomposes, so let's not use ammonium hydroxide. But we can do potassium hydroxide. Potassium hydroxide, strong base or weak base? Strong base. Ammonium hydroxide is a strong base as well. It's tricky because it decomposes into weak base. But this is strong base, weak base, weak base. Why? Solubility. The strong bases are the soluble hydroxides. Otherwise, these aren't very soluble, so the hydroxide is kind of locked up in the crystal lattice. It's not free to react, right? And you have to break apart that lattice to get it to react. This is like, you might have done the sulfate experiment in Chem 1A. Barium chloride is toxic, right? Why is barium chloride toxic? Is it because chloride ions are so toxic? No, the reason barium chloride is toxic is because barium ions, right? And so barium chloride is toxic, but did you know I had to drink barium sulfate? I did a CAT scan, and they wanted me to drink barium sulfate, so I drank barium sulfate. Barium sulfate was a lot like milk and magnesia. It was a paste, you know. It was a paste because barium sulfate, is it very soluble? No. It's not soluble, and it's not that toxic. It's not toxic because yeah, you aren't going to get much barium because the barium is going to be locked in the lattice. This stuff is fairly insoluble, even in very acidic conditions in your stomach. It's not. And so this is okay, this is not okay. Right? And so magnesium there. What about beryllium? Do you know beryllium? You probably don't hear much about beryllium. Do you know why you don't hear much about beryllium? People don't want to work with beryllium. Beryllium used to be very common, especially in the aerospace industry, because magnesium is a very lightweight metal. They can use it. It's lightweight and yet it's fairly strong. Beryllium's the same, but beryllium's even lighter than magnesium. And so at one time in the aerospace industry, they had a lot of machinists working with beryllium metal. But what happened was all those machinists ended up dying, all of them. It turned out beryllium is highly toxic, because the beryllium metal is going to be converted into beryllium ion. And what do you know about beryllium ion? Well, beryllium ion seems like it's similar to magnesium ion. We need magnesium ion, so can I go ahead and substitute beryllium ion instead of magnesium or calcium? Let's say, you know, I ran out of calcium fortified milk. I'm just going to buy some beryllium ion and put that into my water, and I'll get beryllium fortified water. Is that a good idea? Oh, that's a bad idea. This is a bad idea because beryllium is highly toxic. Beryllium is extremely toxic, and so nobody wants to work with this stuff, and this is why you don't see it in the lab. Because the lethal dose, the LD50 on this is very small. You know? And so after all the machinists died, then they were very careful with beryllium. And so we got to learn metathesis properties. These are part of the metathesis properties. You know, why are these? Well, group 1 and ammonium. Group 1 and ammonium are +1 cations. Magnesium is a +2. +2, do you know Coulomb's law? Coulomb's law is going to depend on what? The charge and the size. So neglecting size, this is +2, this is going to have twice as strong of a bond. Iron is a +3, this is going to have 3 times as strong of a bond, right? So the bond is going to be, iron's also quite small. And so those are the types of things that we worry about with metathesis. Metathesis properties are things that we worry. Sometimes people are biased. For example, HF. You know, when people think about HF, they only think about acid properties. But HF, you know, HF, is it a strong acid or weak acid? It's a weak acid. So if you spill some HF on your skin, it's like spilling acetic acid, vinegar on your skin. Is it going to burn much? No, it doesn't burn much. It's a weak acid. You know, if you spilled strong acid, it'd burn a lot more. But it's not the acid properties that are so deadly. HF is a very deadly acid. People do not want to work with HF, just like they do not want to work with beryllium. Why don't we have any HF in the lab? Because it's nasty stuff. What makes it so nasty? Not its acidity. What makes HF so nasty is its metathesis properties. Because what happens is this. The HF will penetrate your flesh until it hits the bone. When it hits the bone, fluoride ions love calcium ions. And fluoride will precipitate out with calcium to make a precipitate of calcium fluoride on your bone, which I heard is extremely painful. when it starts to happen. And it's so painful it could cause death, actually. And so places that work with HF, like at, when I was at UCSB, sometimes I go over to the electrical engineering department. Over at the electrical engineering department, they use HF to etch wafers, right, for circuits. And so I was over there, and on the wall I noticed they have an injection kit. And the injection kit is, if you spill HF on you, of course try to wash it off, but by the time it hits your bone, do you think you can wash it off? No, I mean, it's already penetrated your flesh and washing it off. And so they have injection kits of like calcium, I think it was calcium glutamate. And so you inject yourself with calcium glutamate and then get the calcium levels up in your blood, and hopefully the fluoride precipitates out with the calcium from the injection rather than calcium in your bones. Otherwise, there's serious trouble. And so this is, when we think about this, we think, when I think about chemical properties, it's very simple. I think, what ions, like the question about phosphate, what ions does phosphate like? Well, phosphate's a -3 ion. It's going to like +2 cations and +3 cations. +1 cations, not so much, except for silver. Silver is a +1 cation, and that seems to like to precipitate with things, right? But silver is special because the bonding in silver is much more covalent than ionic. That's a lot of these heavy metals, like lead 4 chloride is molecular. Lead 2 chloride is ionic. And so we think in terms of metathesis. What ions does phosphate like? We think in terms of acid-base. Phosphate turns out to be a base. What acids will it react with? Any acid will react with. We think in terms of redox. Phosphorus is in the +5 oxidation state in phosphate. +5 means it's electron rich or electron poor. +5 means it's lost all its valence electrons. Is it electron rich or electron poor? It's electron poor. Phosphate would be an oxidizer. And so these types of things, this is why we categorize it, and then that covers all your bases. Then you don't have to think, am I missing something? Did I forget to memorize something? No. We hit them all, the 3 types of reactions. And the same thing with HF. We look at its acid-base, it's a weak acid. We look at its metathesis, it loves certain cations, like calcium. We look at its redox properties. And fluoride has special redox properties. H+ has special redox properties, which we'll talk about later when we get to redox. And so that's it. And so this brings us to, things. Obviously this is not comprehensive, but I think I mentioned you can kind of see the pattern. Do you see the pattern? Minus, -2, -3, -2, depends on the charge density, the solubilities. Well, with that said, let's do a little application of metathesis property. HF, Honeywell. Honeywell was a big manufacturer of HF. On the Honeywell website, they had this is like a UCSB. UCSB, they had the wall of horrors. Every single accident they took a picture of and posted it on the wall of horrors. This to prevent additional accidents that they had. Well, Honeywell had the same thing with HF. Some very nasty HF burns and other stuff that they showed on their website, but they took it down because the images, I think, were too gruesome. Some people got HF in their eyes and other stuff. Very. I was just looking for that earlier. I couldn't find it. I'll look for it again if it pops up. But one day my friend called me up. My friend works at JPL, and he bought some surplus vacuum equipment. And he called me up and asked me if he could store it in my garage. And I said, I was reluctant, but I said, okay, what is it? And then he told me what it was. It was just a bunch of stainless steel stuff. But one of the items was a beryllium window. He had a beryllium window. And I said, I don't want a beryllium window in my garage, you know, because I'm just fearful of beryllium. I don't want any beryllium near me because I think the lethal dose is on the level of milligram or microgram. It's very small, so I don't want that. LD50 they call it. It's not that you're going to guarantee to die, but you have a good chance. And it's not acute. It doesn't happen rapidly. It happens over time. And so I refused. Well, what was he using the beryllium window for? Do you know what they use beryllium windows for? Why they have those? Beryllium they use for X-ray windows, you know, and so they can shine X-rays, and the X-rays aren't really scattered much by beryllium window. You know, X-rays get scattered by lots of things, your bones, whatever else, right? Flash. The opposite of beryllium window would be like barium. Why did I take barium in a CAT scan? Do you know why? Barium is good at absorbing X-rays, and so that's why I took it. It's a good imaging agent. It's a good imaging agent because it's got a lot of electrons. Beryllium doesn't have very many electrons, so it's the opposite. They didn't give me a lead cocktail because lead would be even better. Lead has even more electrons. Lead is an excellent absorber of X-rays, right? They make shields, X-ray shields out of lead for the dentist office. And so lead would have been an optimum agent, except the problem with lead is it's so toxic. Even if I took lead sulfate's probably more soluble. And anyway, who wants to consume lead? You know, barium sulfate sounds a lot better to drink. If they give you a cup full of lead sulfate, then would you even want to? No, not even. No. Unfortunately, though, some people do suffer from lead poisoning. This is the other thing I showed you from 1A, but even though I've shown this so many times, it always. This is a CDC report about lead poisoning. You know, and there's some treatments for lead poisoning. These are called chelating agents. The chelating agents go in, and these ions. It's EDTA is an ion. EDTA likes metal cations. So these chelating agents like EDTA bind lead in soft tissue and are used in the treatment of lead poisoning to enhance excretion of lead, thus decreasing the total lead levels in the body. We're going to skip all this other stuff. Actually, there are two. There are two medications. The two medications on the shelf are calcium EDTA and sodium EDTA. Calcium EDTA or sodium EDTA? Which one do you think is more aggressive? Calcium EDTA, the drug, or sodium EDTA? Which one do you think would be more aggressive? Calcium EDTA or sodium EDTA? More aggressive. We're thinking in terms of metathesis. Okay, which one is more aggressive? Sodium hydroxide or magnesium hydroxide? Which one do you think would be more aggressive? Sodium hydroxide, right? Because that's going to free up the hydroxide to let it react. Which one's going to be more aggressive, calcium EDTA or sodium EDTA? Which one's going to free up the EDTA to let it react more? Sodium. Sodium EDTA is more aggressive, right? So I would liken it to this. We have milk of magnesia or drain cleaner. Which one do you want to use? Well, probably milk of magnesia, safer, right? Than drain cleaner, which is sodium hydroxide, sodium EDTA. So let's read the case report here and this one. Texas, February 2005, a girl aged 2 years who was tested for blood lead level during routine health surveillance had a capillary BLL blood lead level of 47 micrograms per deciliter. A venous BLL count of 48 micrograms per deciliter obtained 12 days later confirmed the elevated BLL. A complete blood count and iron study conducted concurrently revealed the low serum iron levels and borderline anemia. On February 28, 2005, the girl was admitted to a local medical center for combined oral and intravenous chelation therapy. The patient's blood electrolytes admission were within normal limits. Initial medication orders included intravenous sodium EDTA and oral Succimer, an agent primarily used for treatment of lead poisoning. The medication order was subsequently corrected by the pediatric resident to intravenous calcium EDTA. At 4:00 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. At 4:35 p.m., she was administered 200 milligrams of oral Succimer. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of intravenous sodium EDTA instead of intravenous calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2 milligrams per deciliter. Normal would be 8.5 to 10.5. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and the cardiac resuscitation code was called at 7:25 a.m. The child had no palpable pulse or audible heartbeat. Repeat laboratory values for serum drawn at 7:55 a.m. indicated that the serum calcium level was less than 5 milligrams per deciliter despite repeated doses of calcium chloride. All attempts at resuscitation failed, and the girl was pronounced dead at 8:12 a.m. Yeah, that, I don't know. Every time I read that, it's hard to read. Pennsylvania, in August 2005, a boy aged 5 years old with autism died while receiving intravenous chelation therapy with sodium EDTA. Oregon, etc. So it goes on and on. Actually, this has happened a lot, and so the CDC, made a recommendation. The CDC, they use sodium EDTA for adults for acute cases of lead poisoning, where lead levels are extreme, and the calcium EDTA is for normal chelation therapy. But what the CDC recommend is to get rid of the sodium. And so there's no more sodium EDTA on the shelves. It's only calcium EDTA, so this mistake can't happen again. But you can see how easy this mistake could happen. I mean, somebody thinks, sodium EDTA, calcium EDTA, what's the difference? It's EDTA, right? But unfortunately, 2-year-old, come on. This is really sad. All right, so we should know about the solubility rules, and we should, as we do it, it's not just memorizing the solubility chart, but it's also trying to think in terms, because sometimes you aren't given stuff on the solubility chart. Like, I don't know, did I say one semester I gave an oxide? I asked the solubility for copper 1 oxide. Did I tell you about that? The student complained to me, oh, it's not on the solubility chart. We didn't have to memorize that one. It's not fair. But they're missing the point. The point is not, memorizing everything. We don't want to. The same thing with the acids chart. You look at the acids. Somebody asked me, should I memorize this? I said, no. There's no need to memorize this. But that doesn't mean that you should never look at it. Some people, when I say don't memorize it, they think, okay, I don't have to even look at this. I don't have to think about this. On the test, that's the only time I'm going to look at it. But that's the wrong way to think about it. The correct way of thinking about it is to read all the entries. What's the strongest acid on the chart? What's the weakest acid on the chart? What's the strongest base on the chart? Do you know what the strongest base on this chart is? What do you think the strongest base on this chart is? Sodium hydroxide? You think that's the strongest base on this chart? No. The strongest base on this chart is probably a bizarre species, is methide. That's the strongest base on this chart. If you go into our classroom, the strongest base in our classroom chart is, I think, amide. Pretty sure it's amide, NH2 minus. But what we should do is, we don't memorize this, but we read this, you know? Periodically, what you do is read all the entries. That way it's in your mind. It's not totally memorized, but at least you've read through it a number of times. And the person who's read through it a number of times, you know, your brain's at work. You know, and your brain's at work trying to make connections between this. You know, your brain's trying to organize this data and understand it. This is a Bronsted chart. Gas formers, we just memorize this. No, this is not comprehensive, but carbonic acid, you know, carbonic acid decomposes into carbon dioxide and water. These first three are unstable. Sulfurous acid decomposes into sulfur dioxide and water. Ammonium hydroxide decomposes into ammonia and water. These three are unstable. So if these three ever form as a product, you got to decompose them immediately, because you can't isolate it in significant quantities. And then we might form things direct, like H2S. This is Rodnay gas. So if you mix acid with sulfide minerals, this is what you get, or sulfide-containing compounds, this is what you get. Hydrogen cyanide is another one. These types of things. There are others. So I guess I must have was talking faster. I don't know how I finished so early. This. Must have forgotten to say something, but it's okay. What we're going to do is we're going to do an in-class exercise. You know, this is review. This metathesis stuff, you know, double replacement. Do you guys remember doing the complete equation, the ionic equation, the net ionic equation? Okay, we want to do that, and then I want you to tell me what the driving force for this reaction is here. You know, what drives this reaction to occur. And so what you're going to do is, I want you to work on this. You could work on this with your neighbor or your friend. And do the complete equation. Let me check it off to make sure the complete equation looks good. And then we'll move on to ionic and net ionic equation. But again, I'd like to do progress checks because I have a certain way I'd like to see it done.